All right, so in this chapter, we're going to be talking about gases, and I always look forward to the end of summer when we have the Great Reno Balloon Race, great demonstration of gases in action. Of course, hot air balloon works because hotter air is hotter gases are less dense than cooler gases, so it's a very simple mechanism for flight. And it's just a really beautiful and fun event. And so what are some properties of gases? That's how we're going to start out. How are they different from liquids and solids? Well, unlike liquids and solids, remember solids have a fixed shape and volume. Liquids have a fixed volume, but a shape that conforms to the container. And gases are sort of the most nebulous of all of them. They'll expand, and so their shape and their volume will expand uniformly to fit that of the container that they're in. As such, they're compressible. So if you shrink in the walls of the container, the gas molecules will get closer to one another, so they're compressible. They have a relatively low density compared to liquids and solids, much actually less dense. And they exert pressure on their surroundings. So you can see like in this container, right, these gas molecules are bouncing around, they're constantly in motion. And every time a molecule hits the wall of the chamber, of the container, that exerts some pressure. And so the total pressure is just the summation of all these different gas particles exerting pressure on the walls of the container. We'll talk a lot about that. There's a lot of different gases that are industrially used. Most of them are going to be relatively small molecules with low molecular weights. We'll talk about that in the intermolecular forces chapter, but higher molecular weights tend to be solids and liquids. There's more forces that bind those molecules together. And so you can see most of these are gases at room temperature, are relatively low molecular weights. Of course, we have the noble gases like helium. We have air that we breathe, so nitrogen, oxygen, and argon. Argon's also a noble gas, but it's about 0.9% argon in just air. And then there's the flammable ones used as fuels, things like acetylene, butane, propane, methane. This is the main component of natural gas in our homes. There's the nitrogen oxides, so nitrous oxide used as an anesthetic, also called laughing gas. There's nitrogen dioxide, it's not on here, but NO2 and NO. All the nitrogen oxides are pretty bad pollutants, components of photochemical smog. There's some other oxides, the carbon oxides, carbon dioxide, carbon monoxide is toxic. Sulfur dioxide, sulfur trioxide is another one, etc. So we'll start with defining what pressure is. Well, pressure, you can think about high and low pressure systems in terms of weather, but that no matter what type of pressure you're talking about, be it the weather or be it inside a small container, that's defined as force divided by area. And so remember that force is mass times acceleration. And so how does that work when you're talking about weather or you're talking about atmospheric pressure? Well, it's just the weight, okay, the mass of all the air above you, this column of air above you extending all the way out into outer space, the weight of that air times acceleration due to gravity, right? Gravitational acceleration constant, 9.8 meters per second. And so that's a force divided by an area, okay? There's a lot of different units that people use for pressure. Force divided by area one, the simplest one is the Pascal, because force, fundamentally, SI unit of force is Newton. So Newton divided by a meter squared, that's a square meter. That's the SI unit, so Pascal. Okay, so we'll use Pascal sometimes. Millimeter mercury, we'll talk about how that works. Millimeter mercury is what's measured out of a barometer, okay, that measures pressure. That's the same unit as torque. Those are exactly the same thing. So 1 millimeter of mercury equals 1 millimeter of torque. My favorite is atmospheres. 1 atmosphere equals 760 torr. And 1 atmosphere is the average pressure, atmospheric pressure at sea level. So that's a very useful unit. Now, if you change your elevation, so if you go up to, let's say, Reno, here we're at 4,500 feet above sea level, we're actually not at 760 torr, we're at about a little bit more than 600 torr. It's just because we're higher up, there's less air above us, and so less pressure. And so this is how the barometer works and where that millimeter of mercury unit comes from. We can also measure in inches of mercury. That would just be the conversion between millimeters and inches being the difference there. And what happens is you have a pool of mercury and you have a vacuum and then you have a glass tube, okay? And what will happen is just that whatever the pressure is of what you're measuring will push down on that pool of mercury and cause it to rise up the tube, okay? The higher it rises up the tube, the higher the pressure. There's more force down, causing this to kind of wick up the tube. And so that's where we get this unit of millimeters of mercury. It's just the height of this tube. And so now we can have just some quick practice of how to interconvert between these all these units. And so let's test. Let's first do scuba diving pressure. It's about 4 atmospheres, depends how far down you are, but let's convert that to millimeters of mercury is what the problem is asking us to do. So all we do very simply there is we take 4.0 atmospheres, that's a given. This is just a simple dimensional analysis. And then we know that 1 atmosphere, for every 1 atmosphere from our unit conversion here, there's 760 torr, which is the same as millimeters of mercury. So we have atmospheres on top, atmospheres on the bottom. We're dividing atmospheres by atmospheres, those cancel. As a result, we get our answer just in millimeters of mercury, which is what we want. And we put that into our calculator and we get 3,040 millimeters of mercury. Okay, so that's this first problem. Now let's do tire pressure. What's 32 psi in millimeters of mercury? Well, we would take, we know from this conversion given to us that for every 14.7 psi, psi, by the way, stands for pounds per square inch. So it's another one of these force divided by area types of pressure units. They all are that, but this unit really shows you that pounds per square inch, just like newtons per square meter. 14.7 psi for every 760 millimeters of mercury. And so if we plug that into our calculator, 32 times 760 divided by 14.7, we get 1,000, rounding to the nearest whole number, 1,654 psi. If I care about sig figs here, which I probably should, I have 2 sig figs and 32, so I should round that to 1 sig fig. So that would be actually 1,700 torr, and that would be so that's sort of just introductory pressure and other aspects of gases for you.